In section 6.3, we're going to talk about orthogonal projections. Now, we did some orthogonal projections in the last section. And if you remember, we did an orthogonal projection onto a vector u. So what this was is we took a vector y and we broke it into its two component pieces. One is in the direction of u, and one is orthogonal to that vector. So the y prime, or the y hat, excuse me, the y hat is the orthogonal projection of y onto u, and the z, we say, is the component that is orthogonal to u. So y hat is this orthogonal projection. We denote that by projection of y onto u. And I won't go through the details, but as long as no matter what u is, as long as u is not the zero vector, we can do it by taking a coefficient times u. Now this coefficient c is going to be the inner product of y and u divided by u inner product with itself. So the coefficient is the thing we need to find, multiply it times u, and that coefficient is going to be inner product of y and u divided by inner product of u with itself. So this is a problem that we did last time, but I just want you to push pause, do it again to figure out what the orthogonal projection is and also the component of y orthogonal to u. All right, so hopefully you went ahead and did that. So the goal is to find the orthogonal projection first. Again, that coefficient is going to be inner product of y and u divided by inner product with u by itself. In this case, inner product of 3, 1 and 1, 1 turns out to be 4. All right, 3 times 1 plus 1 times 1 is 4. Oh, that's bold. And then inner product of u by itself, 1 times 1 plus 1 times 1 gives me 2. So we end up with a coefficient of 2. So the projection of u, or excuse me, the projection of y onto u, projection of y onto u is just going to be 2 times this vector 1, 1, which is obviously the vector 2, 2. All right, so the projection of y onto u is 2, 2, and we can find the component that is orthogonal to u by just taking 3, 1 minus 2, 2. Let me go ahead and do that. The orthogonal component, what we called the z, would have just been basically what's left over again. So what we end up with is the vector 1, negative 1. All right. So there you go. The projection is 2, 2. The z, the orthogonal component, is 1, negative 1. So what we're going to do in this section is extend that idea a little bit further. So just like we broke up y into component parts before, where this y hat was the projection of y onto u, what we're going to do is now we're going to make this y hat a projection onto a subspace, onto W. And we're going to let our orthogonal component, again, be orthogonal to y hat, be orthogonal to that projection. So, in other words, that z is going to be in the orthogonal complement of W. All right? So, we're going to take a projection into some subspace, and then the leftover piece is going to be orthogonal to everything in that subspace. Now here's how we do it. Let's assume we're in a vector space which has an orthogonal basis. That orthogonal basis I'm going to call U1 through U5. And we're going to let W be linear combinations of U1 and U2. All right. So basically what happens is that when I break things up into component parts, if I want my y hat to be inside of W, I want my y hat to be a linear combination of U1 and U2. That means my z is going to be a linear combination of the three other vectors, U3, U4, and U5, from the orthogonal basis. Now, if we do this, what's going to happen, because this is an orthogonal basis, this z, this linear combination, will be orthogonal to the y hat. It'll be orthogonal to U1 and U2. You can check that by just taking an inner product of the z with U1 and seeing that you get 0 because you're taking inner products of U1.U3, U1.U4, U1.U5. And then you can do the same thing with U2 as well. So what you'll get is that because we started with an orthogonal basis, and because we chose W, which was a span of an orthogonal basis, we could break it up like this. Now, notice we have a C1, a C2. It's pretty clear to see that if I force y hat to be a linear combination of U1 and U2, then we're going to get those coefficients just like we did when we projected onto U. You just take y inner product with whatever U divided by U, whatever U inner product with itself. So that's it. That's the orthogonal projection onto a subspace W. Now, W is going to be a subspace, so it's going to be a span of things. And notice that we do have to start with an orthogonal basis for W in order to make this work. And there we go. By the way, this y hat is the orthogonal projection of y onto subspace W. We denote that in almost the identical way we did before, projection of y onto W. So instead of onto U, now we're onto W. And from what we took away from earlier, this is the y hat. So let's do one of these. Let's say y is 2, 5, 6, and W is the span of 2, 1, 1. So W is a one-dimensional subspace of R3. Let's find the projection of y onto W, and then find the component of y that's orthogonal to w. Now, if you do this, then what you're going to end up with, so this is a one-dimensional vector space. What I'm going to be trying to do, projecting onto w, is figure out a linear combination of this vector, so basically just a scalar times this vector, which is the component in that direction. So notice that this is exactly what we did before. So in order to find that coefficient, it's just going to be inner product of y with this vector 2, 1, 1. By the way, if you do that, 2 times 2 is 4, 5 times 1 is 5, 6 times 1 is 6. So I'm sorry, 2 times 1. Whew, I said that wrong. 2 times 2 is 4. 5 times 1 is 5. 6 times 1 is 6. So the coefficient on top is going to be 15. On bottom, we're just going to take the inner product of 2, 1, 1 with itself. 2 times 2 is 4. 1 times 1 is 1. 1 times 1 again is 1 again. So what you get is you end up with 15 over 6, which is equal to 2.5. All right. Now what that means is that the projection of y onto w is going to be 2.5 times this vector. Sorry, I've left up my last example, so 2.5 times that vector, which, is equal to, so 2.5 times 2 gives me 5. 2.5 times 1 gives me 2.5. 2.5 times 1 gives me another 2.5. So there we go. That's the projection of y onto w. And really what that is just a projection of y onto the basis elements of w, so long as w has an orthogonal basis. Now, if you're looking for the z, if you're looking for the component of y, which is orthogonal to this projection, you're going to take 2, 5, 6, and subtract off 5, 2.5, 2.5. So what you get, 2 minus 5 is negative 3. 5 minus 2.5 is 2.5. And then 6 minus 2.5 is 3.5. So there you go, negative 3, 2.5, 3.5 should be the component of y, which is orthogonal to your projection, or orthogonal to w. By the way, you can check that by just doing 2, 1, 1 inner product with this. So if you think, take the inner product, if you want to check yourself that you've done it right, you just take the orthogonal component, inner product with 2, 1, 1, and you get negative 6 plus 2.5 plus 3.5, which is in fact 0. So that's just shows you that our orthogonal component is in fact orthogonal to every vector in the subspace. Since it's orthogonal to the basis element, it's orthogonal to every vector in the subspace, in the span. All right, so that's the idea. Now, obviously, this was exactly the same as projecting onto a U, where U was our vector 2, 1, 1. But sometimes it's going to take a couple of projections. We're going to have to project onto a U1 and project onto a U2, and my y hat, or my projection of y onto W, will be the sum of those two. So that's what we're going to do now. Let's try to project 745 onto the subspace created, the subspace which is the span of 1, 2, 1 and 1, 0, negative 1. So I want you to go ahead and do the projection and then find the component of y that's orthogonal to W. So push pause on the video and try that out. All right, so as I get started, the one thing I need to do is make sure that these two vectors in the span of, in the basis for W, this 1, 2, 1, and 1, 0, negative 1, I gotta make sure that they are orthogonal. In this case, when I take the inner product, I get 1, 0, negative 1, that adds to 0. So these two vectors are orthogonal, and therefore they form an orthogonal basis for W. So once we know that, then we can go through and project Y onto W. Now when we project 745 onto W, basically we're going to see what linear combination of elements from W can get me essentially as close as I can to 745. These coefficients, again, because I'm using orthogonal basis, I can find the coefficients by doing inner product of y with u1 divided by u1 dot u1. Again, where u1 is my basis element 1, 2, 1. And I would do the same thing with u2 as well. With, again, my basis vector here is 1, 0, negative 1 when I deal with the u2. All right, so let's find that coefficient. What we see here, 7 times 1 is 7. Oops. 7 times 1 is 7. 4 times 2 is 8. 5 times 1 is 5. So my numerator is going to be that. My denominator, u1 multiplied times itself, I get 1 plus 4 plus 1. I say multiply, I really mean inner product with itself. So 7 plus 8 plus 5 gives me a 20 over 1 plus 4 plus 1 is a 6. All right, so what do we get? 10 thirds there? There we go. 10 thirds is the coefficient of u1. Now, if you do the same thing for u2, we can find the coefficient, inner product y with u2. 7 times 1 is 7. 4 times 0 is 0. 5 times negative 1 minus 5. And then u2 inner product with itself is 1 plus 0 plus 1. So we end up with 2 over 2, which is just 1. Okay, so that's what I get. Hopefully I've done my calculations right, and most of these I've been doing in my head. So hopefully I've done those calculations right. And if I have, well then I've found the projection. Now, remember the projection is coefficient times this vector. We found that coefficient to be 10/3 plus coefficient times that vector. We found that coefficient to be 1. And basically, I just need to add these two things together. 10/3 times 1 plus 1 times 1 gives me either 4 1/3 or 13 over 3. Doesn't matter. I'm going to write that as 13 over 3. 10/3 times 2 plus 1 times 0 ends up as a 20 over 3. And then 10/3 times 1 plus 1 times -1 gives me a 2 1/3, or in other words, 7 over 3. So that's the projection onto y. I said of y onto w. Excuse me. Now, when you get that, hopefully I've calculated everything correctly. When you get that, you can take your original vector, which was 7, 4, 5, subtract off what I just found, 13/3, 20/3, 7/3, and it'll give you a vector. Let's just which in this case is 8/3, -8/3, and again an 8/3. Okay, so it'll give me this vector. Now, this vector, z, is the vector which is orthogonal to my original subspace up here. So if you actually go ahead and do the calculations, you'd see that the inner product of the vector z with 1, 2, 1 would give you 0, and the inner product of vector z with 1, 0, -1 would also give you 0. So what we've done is we've broken down y into two pieces. The projection, 13 over 3, 20 over 3, 7 over 3, and the orthogonal component, 8/3, -8/3, 8/3, which, when you add them up, add to our starting vector of 7, 4, 5. So there you go. That's how to do orthogonal projections onto spans of, a dimension 2 subspace. Excuse me. All right, there it is. So I want you to go ahead, push pause on the video, and do the same thing. We're utilizing the same subspace W. I want you to find the projection of 3, 8, 5 onto W, and then find the component of y, which is orthogonal to w. All right, so we're projecting 385 onto w, and we're going to find the component which is orthogonal to w. So same manner we did last time. In fact, the w's are the same. So 1, 2, 1 and 1, 0, negative 1 are orthogonal to each other. We know that. We want to find the coefficients. So all we have to do to find the coefficients, we'll do this one at a time. We'll call 1, 2, 1 the u1 again. When I do inner product of y with u1, I get 3. 8 times 2 is 16. 5 times 1 is 5. So 3 plus 16 plus 5 gives you 24. And then when you do u1 inner product with itself, 1 times 1 is 1. 2 times 2 is 4. 1 times 1 is 1. So you get 24 over 6, which is a 4. So my coefficient of u1 should be 4. When I deal with the coefficient of u2, 3 times 1 is 3. 8 times 0 is 0. 5 times negative 1 is negative 5. u2, inner product with itself, 1 times 1 is 1. 0 times 0 is 0. Negative 1 times negative 1 is a positive 1. So we get negative 2 over 2, which is a negative 1. Now, what this means for the projection of y onto w is that that projection is going to be the linear combination 4 times my u1 minus 1 times my u2. When you calculate that, 4 times 1 minus 1 times 1 gives me a 3. 4 times 2 is 8, minus 0 is 8. And then 4 times 1 is 4. Minus 1 times minus 1 is a plus 1. So 4 plus 1 is 5. Now that's kind of a strange thing. My projection of 385 onto W came out as 385. And my Z, well, my orthogonal component would just be 0, 0, 0. Now, what's actually happening here in this situation is that 385 is a linear combination of my basis elements from W. Therefore, 385 is actually a vector which is in W. And so this is what happens when your vector is in W. By the way, a similar thing would have happened last time when we dealt with 2 dimensions if y and our u were on the same line, if they were just scalar multiples of each other. So let me just kind of visualize that. Now I'm going to visualize this in 2 dimensions, but basically last time we were projecting things like 2, 4 onto 6, 3. But basically if I were to ask you to project, let's say 4, 2, I can't get it very well, onto 6, 3, well 4, 2 and 6, 3 are in the same direction. So projecting 4, 2 onto 6, 3 would have just given me 4, 2. And then the orthogonal component, it would have been the 0 vector because I don't have to move anywhere. So there you go. So if these are in a line, then those types of things happen. I'll try to explain a little bit of that in detail later, but there we go. Now you can do this in any dimension you want. So I want you to push pause and find the projection of y onto this W and then find the component of y orthogonal to w. So we're going to start this. Now I'm going to follow the same, it's going to be the exact same procedure. Obviously now our vectors are in 4 dimensions instead of 3, but the procedure is exactly the same. I'm thinking of writing linear combination, oops, that should be a plus, linear combination of the 2 basis elements from W. Now, notice I do want to point out again that these 2 vectors in W, this is an orthogonal basis. This does not work if the basis is not orthogonal. So since we have an orthogonal basis, 1, 1, 0, 0, and 0, 0, 4, 1 are orthogonal to each other, I can do this trick. So let's find the coefficient of C1. That's going to require me to do an inner product of y with U1. And so we're going to go 7 times 1, 7 times 1, 7 times 0, 7 times 0. What you get is 7 plus 7 plus 0 plus 0. Again, that's just the number 7. So you get 14. And then inner product of U1 with itself is 1 plus 1 plus 0 plus 0. So what we end up with is 14 over 2, which we simplify to 7. So the coefficient C1 is going to be 7. Now we do the same thing for our other vector. Inner product, 7 times 0 is 0. Make sure that doesn't show up bold. Plus 0 plus, well, in this case, 28. 7 times 4 is 28. 7 times 1 is 7. So we end up a numerator, which is going to be 35. Our denominator, we're going to take 4 times 4 plus 1 times 1. So our denominator is going to end up as a 17. Now that's kind of an ugly fraction, but that's still perfectly legitimate for a real number coefficient. So there you go, 35 over 17. So the projection of y onto w is going to be 7 times 1100 and 35 over 17 times 0041. By the way, what you get there is 7, 7. 35 over 17 times 4. I haven't calculated that yet, but my calculator can get it. I got 140 over 17. Or if you'd rather, you can call that 8. Yeah, you can call that 8 and whatever 17ths it is, whatever the leftover is. Okay, and then obviously 35 over 17 is my last value there. Okay, so that's the projection. It's kind of an ugly one. We get ugly fractions, but that's the way it goes. Now, by the way, when you're posting things into Moodle, you will probably round that to a couple of decimal places. So you'd probably call that 8.24 or something like that when you type in your answer into Moodle. And you'd call 35 over 17 2.06 or something like that. So let's go check this out. When we find the orthogonal component, all I have to do is this. So what we get is a 0, 0. Now when you take 7 minus 140 divided by 17, I got negative 1.235, etc., 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 which was negative 21 over 17. And when you do the same thing, 7 minus 35 over 17, you get 84 over 17. Okay, so that is the orthogonal component. It's the projection of y onto w, and z is the orthogonal component to that projection. And once again, if you actually went ahead and looked at doing the inner product of that z with either one of my basis elements up here, you'll see that when you do it, you get 0 in both cases. So that z is guaranteed to be orthogonal to the basis elements in there. So I want you to try try one more projection onto a subspace of dimension 2. Go ahead and push pause on the video and try it out. Okay, now again, before we get started, we got to make sure these basis elements are orthogonal. In other words, the basis is an orthogonal set, and in this case it is. So then we can move on and start finding our projection. Our projection is going to be a linear combination of these two basis elements, and the coefficients are going to come from doing inner product of y with the u1 and y with u2, and then dividing by u1.u1, and in this case u2.u2. So let's start with coefficient on u1. Now u1 I'm calling the 1110 vector. So if you do inner product with y, u1, you get 1 plus 4 plus 5, which is just a 10. Now if I do u1 inner product with itself, I get 1 plus 1 plus 1 plus 0. I get 3. So 10/3 is my coefficient. That doesn't actually simplify. When I do y inner product with u2, I'm going to get 1 times 0 is 0, negative 4, 5, negative 4. So that is going to be a negative 3 if I've done my calculations right. And then u2 dot u2, we're going to get negative 1 times negative 1 is a positive 1, plus 1 times 1 is 1, plus 2 times 2 is 4, and then we get a 6 on the bottom. So I'm getting out that my coefficient 2 is a negative 0.5. So my projection of y onto w is 10/3 times 1110 plus a negative 0.5 times 0, negative 1, 1, 2. All right, and then we just figure out what that is. 10 thirds times 1 minus 0.5 times 0. Let me double check that I got the right vector there. Yep. So we get 10 thirds is the first entry. When you take 10 thirds times 1 minus 0.5 times -1, you get 23 over 6. By the way, that's going to be 10 thirds plus a half. And then 10 thirds minus a half is 17 over 6. And then 10 thirds times 0 is 0. Minus 0.5 times 2 is -1. Okay, so that is the projection of y onto w. Once I have that, I can find the orthogonal components. 10 thirds, 23 over 6, 17 over 6. Oops. 17 over 6. And then -1. So I can find the orthogonal component by just taking my original vector minus my projection. And so there we go. We're going to get -7 thirds. When I take 4 minus 23 over 6, I get 1/6. When I take 5 minus 17 over 6, I end up with 2 1/6, or 13 over 6. And then lastly, -2 minus a -1 gives me a -1. All right. Now again, this looks fairly messy. We end up with some ugly fractions, but you can see what's going on. They're not so hard that you can't deal with them. Hopefully you remember where that fraction decimal button is on your calculator so that you can use that when necessary. And by the way, again, you can always double check that this z that we found is indeed orthogonal to both vectors in W. Or I should say, both vectors in the orthogonal basis for W. Now the last thing I want to do in this section is just, well, I should say, the last example we're going to do of projections in this section is going to be projecting onto a dimension 3 subspace. So if you take a look at these 3 vectors, it turns out these 3 vectors are an orthogonal set. So these 3 vectors, 1, 1, 1, 0, 0, -1, 1, 2, and -2, 1, 1, 0, all form an orthogonal basis for W. So I would like you to use what we did before to project 1, 4, 5, -2 onto this W. Again, you can utilize our last example because notice that the first 2 vectors in our previous example, well, we're dealing with the same y, and then the first 2 vectors in the previous example are the same as the first 2 vectors in this example. So go ahead, use the previous example and expand that to this W. push pause on the video and do your calculations. So here we go. So in my last example, I did this W. Now I'm going to add one dimension by adding a vector to the basis of W. So my vector I'm adding is -2, 1, 1, 0. Now my projection now onto this W, I probably should have used different letters because, again, we're kind of redundant, but all I have to do is add a third component. Now notice that the coefficient of 1, 1, 1 is not going to change. It's still going to be obtained by taking y and u1 inner product divided by u1 inner product with itself. So I'm still going to get 10/3 as the coefficient for u1, and the same thing for u2. u2, I already calculated that. I already calculated the coefficient of u2, and we've already found it to be -0.5. So the coefficient on my u1 is not going to change, and this shows that the coefficient on my u2 is not going to change. So all I need to do is calculate the coefficient on u3, and I do that in the same way. Inner product of y with u3 divided by u3 inner product with itself. So let's take this, that's a -2 plus 4 plus 5 plus 0. So what I get on top is a 7 divided by u3 dot u3. I'm going to get -2 times -2 is a 4 plus 1 times 1 is 1 plus 1 times 1 is 1 plus 0 times 0 is 0. So I got 7/6. No good way to simplify that. So my coefficient on u3 is 7/6. Now again, what I'm doing is I'm just figuring out the coefficients to use in order to add those things up. So what we do is we take our projection. My first coefficient was 10/3, so 10/3 times u1. My second coefficient was -0.5. If you'd rather write that as -1/2, that's no big deal either. And my third coefficient we just found is 7/6. Now when you add all those things up, the projection of y onto w is going to be equal to, well, 1, 5, 4, -1. All right, kind of turned out fairly nicely there. Magically, you get all these fractions, these awkward looking fractions in here, but they all just cancel each other out nicely, and you end up with whole numbers when you do your projection. Again, that doesn't always happen. We saw in the last example, we didn't get all whole numbers. But our projection of y onto w is a really nice vector, 1, 5, 4, -1. If I want to find the orthogonal component to that, all I have to do is start with my original y, 1, 4, 5, -2. Write in 1, 5, 4, -1. We're going to subtract those. 1 minus 1 is 0. 4 minus 5 is -1. 5 minus 4 is a +1. -2 minus 1 is a -1. All right, so that's what z is. your component, which is orthogonal. Z is that vector there. 0, -1, 1, -1. Now, if we've done this right, you should be able to go back up to W and show that the Z is in the orthogonal complement of W. So just take that Z we found, inner product it with all three of these basis elements, and you can check your work and see that you, in fact, do get 0. So we came up with the Z, which is, in fact, orthogonal to our set W. So there you go. Now, I want to take a moment to just think about what really is happening geometrically in Rn. Okay, we did this last time with R2, but we're going to also think of this in R3 as well. So let me remind you of what happened in R2. So when we projected onto a vector, let's say we were projecting 2, 4 onto 6, 3, what we would have done, whoops, something's off here. There we go. What we would have done is broken up 2, 4 into two component parts. Let me stop here for a second. There we go. Zoom in a little bit. So we would have broken up 2, 4 into vectors which add up to 2, 4. So what we would have done is we would have taken one vector along the same direction as 6, 3. And if I've drawn this fairly accurately, then my next vector, when I put it tip to end here, should create a right triangle. This might be a little bit off. I kind of clicked on the right spot. So this here is my projection, and this is my orthogonal component. So we're projecting it onto the 6, 3. Now we're using an orthogonal component. Now, if I'm not projecting onto a specific vector, but let's say onto the subspace that's generated by 6, 3, well, the subspace that's generated by 6, 3 is basically any vector that's along the same line. There's really no difference. So I just clicked and made that go on as far as I can reach, or at least beyond my graph. So there's really no difference in the orthogonal projection. By the way, if this were real, I would have also went down and to the left as well, but this graphing feature doesn't do that very well. So again, whoops, what we're up to is we got one vector along the line, and the other vector, when I draw up here, is going to create an two orthogonal vectors. My projection, that's this one, and my z, which is this one. So my projection is this vector, my z is that vector. Now, that's what happens in R2. In R3, it's going to be a little bit harder to see. So let me pull that up. All right, so what we've done here is I've looked up online. You can just Google search for a picture of 3D coordinate system. Now, in this case, my W's might be, for instance, if it were two-dimensional, the span of two vectors would give a plane. And so if you notice, this outline here, that gives me some plane through the origin, okay? So we have this plane through the origin. That would be a two-dimensional subspace for, let's say, W, subspace W. Now, if we had a vector from the origin in some direction, let's say we did something like that. What we're doing when we project onto W is we're taking a vector in W and then we're taking the orthogonal part like that. Again, this little black vector here is supposed to be my projection. So I'm just going to write P for projection. And then my Z is the other black vector. And again, it's kind of hard to see because I can't rotate this picture. But this projection would be in that plane, somewhere in that plane, and the Z is going to be orthogonal or perpendicular to that plane. Okay, so again, my starting vector Y is the red one. And then my projection is in W, and then a perpendicular or orthogonal vector out of that subspace. So in R3, that's what's happening. Now, because of this, the one thing you'll notice is that wherever this projection lands in subspace W, that's going to be actually the closest point because of the orthogonality. It's going to be the closest point to Y in W. And that's what our next slide says. There's something called the best approximation theorem. So the projection of Y onto W is the closest vector or the closest point in W to the vector or point Y. Again, whether you're thinking about Y as the vector itself or the endpoint, the projection of Y onto W is going to be my closest point in W to the point Y or to the vector Y. And that's all this says, that Y prime, the length of Y hat minus Y is less than or equal to V minus Y for any vector in W. Okay? I don't deal with the best approximation theorem a whole lot. I'm not going to ask you about that on Moodle or the test, but it is something to notice. Now, the one thing that we had in all of this section was the fact that our W was a span of some basis which was orthogonal. So every time we dealt with a W, we always had an orthogonal basis. So like in this example, when we projected 7, 4, 5 onto W, the span of W, the span was 1, 2, 1, and 1, 0, negative 1, or linear combinations of those two. But those two vectors themselves were orthogonal. And even when we had 3 dimensions for our W, this set here, which forms a basis for W, is an orthogonal set. And so what we're going to do in the next section is we're going to say, well, what's going to happen if my basis for W doesn't start out as orthogonal? What if I want to project onto this W, but this W does not have an orthogonal, or excuse me, this W, I'm not given an orthogonal basis for it. And if I'm not given an orthogonal basis for W, then what we're going to do in the next section is create an orthogonal basis for W. And that thing is called the Gram-Schmidt process. So we'll see more of that in the next section. But for now, being able to do these projections is just is all we want to do in 6.3.